that involves arc trig and arc hyperbolic functions. So we looked at some examples yesterday and we will continue today. Just see this. Let me see if I can fix this. Just give me a minute and get it back. Okay, I think it's fine now. Right, so let's see our next example. Here we have been asked to, call this one number 1, we have to integrate hyperbolic sec of x with respect to x. Okay, so this one, when you want to integrate it first, or one of the things that you could do is you can write it in terms of the hyperbolic cos, and doing that, this is the integral of 1 over the hyperbolic cos of x dx. Okay, now the way that it is still not that easy to integrate just the way that it is. So what we can do is we can multiply by the hyperbolic cos over the hyperbolic cos, which is 1. So that doesn't change the question. So we have the integral here. Let me just write. So what we do is say cos over hyperbolic cos x, then what we get is hyperbolic cos of x over hyperbolic cos of x squared in the denominator, like that. Okay, and then the hyperbolic cos of x, we know that is equal to 1 plus the hyperbolic sign, because hyperbolic cos minus hyperbolic sine squared is equal to 1. So if you make the hyperbolic cos squared a subject of the formula, you get the integral cos hyperbolic 1 plus sine hyperbolic squared of x dx. So you can see here I have 1 plus something squared, and the derivative of that something is what I have in the numerator. So I need to use tan inverse. Okay, so this this is already in the form that I want. I don't need to add any constants. Like I say, the derivative of the hyperbolic sign is just hyperbolic cos. So I can just write this as tan inverse of hyperbolic cos of x plus c. Okay, so sometimes you will have to introduce terms into whatever it is that you're integrating in order to have it in the form that you want, so you can use Arc Trig integration. And we look at some of the questions from exercise. Yeah.
I'm a bit confused. At your last step, isn't when you supposed to say the derivative of the denominator is 2 cos hx?
No. This is in the form. Let me see. What I have here is something like this: u prime over 1 plus u squared du. This is what I have. So when it's like this, this is just tan inverse of u, not u squared. So it's not the derivative of sine hyperbolic squared, it's the derivative of sine hyperbolic.
Oh.
Okay. Then we have exercise 4.1.7. Okay, so there is a lot of questions in that exercise. I only picked a few to do. The other ones are for you to practice. And as I always say, it is very important that you must practice. That is the key to this course, especially because there is a lot of techniques and formulas that you need to remember. You remember the formulas by using them, and you use them over and over again. Okay, so first we look at number 2. Number 2 is the integral of dx over the square root of 16 plus 3x squared. Okay, so we want to have this in the form that will allow us to use Arc Trig. So we know with our Arc Trig, it's always 1 plus something squared. So we have to get rid of the 16 by factoring it out. So when we do that, we have the integral dx over the square root. So you factorize out the 16, you have 1 plus 3 over 16 x squared, and this is over dx. And then this square root of 16, which is 4, can go outside. So I have 1 over 4, the integral of dx over the square root of 1 plus, okay, and then this 3 over 16, we want to include it with the square, because with our functions, it is always 1 plus something squared, so it must be a whole term that is being squared. So 3 over 16, its square root is the square root of 3 over 4. So this is the square root of 3 over 4 times x, and then the whole thing is being squared, and this is over dx. Oh, dx is in the numerator. Okay, so now that I have it in the form that I want, here you just need to decide, is the sine inverse, hyperbolic sine inverse, tan inverse, and so on. So whenever we have a square root, already tan and cot are out, whether it's the hyperbolic or the normal one. So here we have 1 plus. So if this was just normal sine, then we would have minus, but because we have a plus, this is a hyperbolic sine. Okay, so in our minds, we should know we're going to have a hyperbolic sine, but here in the numerator, we need to have the derivative of this thing that we have in brackets. The derivative of 3, the square root of 3 over 4x is just square root of 3 over 4. So I need to put a square root of 3 over 4 here, and then some other number here, so that when I multiply the number I put outside and the square root of 3 over 4 there, I still end up with 1 over 4. So to do that, we said on top I will put the square root of 3 over 4 dx, square root of 1 plus the square root of 3 over 4 times x. Okay, so here I just say 1 over 4 divided by the square root of 3 over 4, which is 1 over the square root of 3. Okay, so again, you can try multiplying 1 over the square root of 3 times square root of 3 over 4, you get 1 over 4, which is the one that was outside. So we haven't changed anything, but what we have inside the integral is now in the form that we wanted, and we've already said that this is the hyperbolic sine inverse. So this is 1 over square root of 3 hyperbolic sine inverse of the square root of 3 over 4x, and then you add your constant of integration. And
Ma'am.
yeah.
Yes. Don't you
Yeah.
have to split it again?
Don't I have to do what?
To square it, the second last step.
Don't I have to do what?
To square it.
Square it. Yes, the square should still be there. Yes. Then the third one, or number 3 in the exercise, we have dx over 5 minus 4x squared. Okay, so here, again, we want 1 minus something squared. So this 5 over here, we have to get rid of it. So we will factor out the 5. So we have dx, the integral of dx over 5, 1 minus 4 over 5 x squared. Okay, and this 1 over 5 can come outside, and we need to include this 4 over 5 as part of the square. So what we have is 1 over 5, the integral dx over 1 minus 2 over the square root of 5x squared, like that. Okay, so the denominator is now in the form that we like. Okay, so the denominator is in the form that we like. Now our numerator over here has to be the derivative of whatever it is we're squaring here. So the derivative of what we're squaring here is 2 over the square root of 5. So we need to put a 2 over the square root of 5 here and something outside so that when it multiplies with the 2 over the square root of 5, we still end up with 1 over 5. So here we have 2 over the square root of 5 dx in the numerator, 1 minus 2 over the square root of 5x must be squared. And then to find out what we put here, we just say 1 over 5 divided by 2 over the square root of 5. So that is square root of 5 over 10. Okay, so again, if I multiply these two, the square root of 5s will cancel. I'll have 2 over 10, which is 1 over 5 that I have over there. Okay, so everything is set. I can just integrate this. So here I have 1 minus, there's no square root, so it's either cot or tan, hyperbolic or not. So here I have 1 minus this, so this is just hyperbolic tan, and this is the square root of 5 over 10, the hyperbolic tan inverse of 2 over the square root of 5x, and then you add your constant of integration. And number 6, the integral. This one is a definite integral. Remember, when you get your definite integral, you must substitute your limits at the end. So this is dx over 7 plus x squared. Okay, so first our denominator must be in the form that we want, which is 1 plus something squared. So we need to get rid of the 7. We factorize it out. So this is the integral from 1 to 2. We have dx, factor out the 7, 1 plus x squared over 7. Okay, and then the 1 over 7 can come out, and then this 7 must be included in the square. So we have 1 over 7, the integral 1 to 2, we have dx in the numerator, and then in the denominator we have 1 plus x over the square root of 7 squared. Okay, so the only thing left is our numerator over here must be the derivative of whatever it is we're squaring there. So the derivative is 1 over square root of 7. So this is 1 over the square root of 7 dx, and then 1 plus x over the square root of 7 squared, and here we will have 1 over the square root of 7, so that when we multiply this and that, we still end up with 1 over 7. Okay, so this is exactly in the form that we want, so we can just integrate this, and then we will get 1 over the square root of 7, and this is tan inverse of x over the square root of 7. Okay, with our limits there, 1 to 2. So now we substitute our limits. This is 1 over the square root of 7, tan inverse of 2 over the square root of 7 minus tan inverse of 1 over the square root of 7. Okay, so we get 6.192. And here my calculator is in degree mode. Okay, so this should be degrees. That was number 6, a definite integral. Then number 11. Of the integral of x to the power of 3 over 4 plus x to the power of 8. Okay, so again here dx. So again here we do the same thing. Let's see, let me check if I copied this question correctly. Okay. Okay. Right, so the way we do this one, again, we want 1 plus something to the power of 2 over here. So this 4 here, we have to factor it out. So in the numerator, we have x to the power of 3 over 4, 1 plus x to the power of 8 over 4. Okay, so this term here, we have to write it as a square, so something squared. So this is going to be the integral of x to the power of 3 over 4. Let me just take the 1 over 4 outside. So okay, so 1 over 4, and then I have 1 plus x to the power of 4 over 2 squared. Okay, so what we always want is to have 1 here can be plus or minus, but this term here must be squared. Okay, and then our numerator must be the derivative of the denominator. So you can see if I differentiate the denominator, I get 2x to the power of 3. So there's a 2 missing over here. So I will add it 2 and then multiply by half outside. And this gives me 1 over 8. The integral of 2x cubed dx over 1 plus x to the power of 4 over 2 squared. Okay, so now it is exactly in the form that I want. This is a plus here, so that will be tan inverse. There's no square roots. So this is 1 over 8 tan inverse of x to the power of 4 over 2 plus our constant of integration. And number 15, we have cos x over the square root of sine squared x minus 1 dx. Okay, so you can see here in the denominator, this is sine x squared, and the derivative of sine is cos. Sorry, I didn't copy the question correctly. It's 9 here. Okay, so like that. So first thing, this 9 over here, we have to make it a 1. And this is the integral cos x over square root 9. Here we have sine squared x over 9 minus 1. Everything is under the square root like that, dx. So this square root of 9, which is 1 over 3, can go outside. So we have 1 over 3 integral of cos x dx over the square root. And then this 9, we want to make it part of the square. So this is sine x over 3, the whole thing squared minus 1. Okay, so now this is in the form that we want. The denominator, we have something squared minus 1, and that is the hyperbolic cos inverse. Yeah, hyperbolic cos inverse. Okay, so the only thing is we need to check that the numerator is the derivative of the denominator. So the denominator here, we have sine x over 3. If we differentiate that, we have cos x over 3. So this 1 over 3 should just go here, and we have cos x over 3, and then the integral will just be the hyperbolic cos inverse of what we have over here. So we need to rewrite this as the integral of cos x over 3 dx over the square root sine x over 3 squared minus 1. Okay, so it's in the form that we want. There are no constants outside, and the solution to that is hyperbolic cos inverse of sine x over 3 plus c. Sorry. Plus c, like that. And into number 23. Number 23 is a definite integral, so we're integrating from 2 to 4. We have dx over the square root of 6x minus 8 minus x squared. So we said whenever you have a quadratic expression in this form, what you need to do is complete the square and then have it with 1 plus or minus something squared. Okay, so first step is to complete the square over here. Excuse me. This is the integral from 2 to 4. we have dx in the numerator, and then in the denominator, when we complete the square, we look at these two numbers, you have minus outside, then x, then minus 6 divided by 2 will give me minus 3. You close the bracket, and then here you would add 9, which is the square of this. So we have 9 plus negative 8, which is 1. Okay, so we've completed the square over here, and then we can write it properly in the form that we want. This is the integral from 2 to 4. We have dx in the numerator, and then we have 1 minus x minus 3 squared, like that. Okay, so we just need to check, is the numerator the derivative of whatever it is we're squaring here? The derivative of x minus 3 is 1, so the numerator is fine, so we can just go ahead and integrate. So we have a square root, we should be thinking sine and cos, and because this is minus 1 minus something, this is sine inverse or negative cos inverse. So this is sine inverse of x minus 3, and then we add our constant of, no, don't add the constant of integration because this is a definite integral. Okay, then we integrate from 2 to 4. So this is sine inverse 4 minus 3 is 1. Then sine inverse of 2 minus 3, which is minus 1. Okay, so here sine inverse of 1 is 90 or pi radians, depending on, or pi over 2 radians rather. So here, let's put 90 degrees. And then minus sine inverse of 1, of negative 1 rather, that is 270. Is that right? Yeah. Okay, so 4 minus 3. Okay, here. Or just type it in on your calculator like that. Let's see why. Sine inverse of minus 1. Okay, so here this gives me negative 180. Let's see if it did. Okay. Okay. This gives me negative 180 degrees.
Yes, I get positive 180.
Yeah, you on your calculator you do get positive 180, but if you are doing it this way, The answer should be positive 180. I think sine of 180 and sine of minus 180 are the same. So I guess that's why your calculator would give you the positive one. Yeah.
Isn't it because they use that identity sine open bracket minus 1 is the same as minus sine open bracket 1?
But here we're not doing sine. This is sine inverse.
What? Same thing?
Because here it's sine inverse of 1. Or does the identity say that it is minus sine inverse?
Sine. It says sine.
Is
Not
it not the same, like saying 90 degrees plus 90 degrees?
Let me see. Okay, I would take the answer on your calculator. I know that sine inverse of minus 1 is equal to 270. So yeah, I need to think about that one, how we would actually justify saying that this is minus 180, but minus 180 is the same as 180 because they are at the same position. Just measure one clockwise and the other one anti-clockwise, I suppose. So this would give 180 degrees. Yeah. Okay, that was number 23. Then what was the next one? Number 25. Number 25, we have the integral of 2x minus 3 over the square root of x squared minus 2x plus 5 dx. Okay, so this is what we have to integrate. So we say that whenever your numerator is a linear term like this, what you want to do is you want to split it up in such a way that the first part will give you a numerator. Somebody's mic is muted. Please mute your mic. Erasmus.
Antarctica o continente.
Erasmus, we're waiting for you.
Antarctica ngokwengumu ulina wako shiome. Continente. Yeah. Omia. Antarctica o continente ai anigwa porque haisa. Ngerongesh ke watara oleda ino Africa. Aye. Just the ice. It's a polar region. Oh, guy, did I uko bengwera karen ngeshimbuya wali koma sipunge mbuwa zilira kwa South Africa. That A is from the alternative.
Nathan, I think
Mwono mwapa mwigengano ni note.
you can just mute him yourself.
Utaiteni.
Only you can.
No. He must mute himself.
Iceberg. Yeah. Na ocho nini mani ngwapo nga. Yeah. Nina ndepora ijeve ngumuko kwa tone. Shashini mambio ya fikendi tu. It's too much. Ngomeoge ngumuka. That's why climate what? That's why anwaka badharo kukiri bende kuroka honi na yeah. Yeah.
I'm waiting for him to mute himself.
Oh.
Thank you. All right, so now we can continue. So we said that when you have a fraction like this, what you want to do is you want to split up the numerator so that one part is the derivative of the denominator, and then the other part is something that you can then rewrite so that you use the Arc Trig integration. So here, if I look at what I have, the derivative of the denominator is 2x minus 2, but here I have 2x minus 3. So I can split this as 2x minus 2 minus 1. So this is the integral of 2x minus 3 minus 2 minus 1 over x squared minus 2x plus 5 dx. Okay, and then we write this as two fractions. One part will take the derivative of the denominator, and then the other part will have minus 1 over the square root of this.
Miss.
Yeah.
Where is the microphone coming from?
From here, from the 3.
Oh, okay, yes.
Okay, so I have the integral of 2x minus 2 over the square root of x squared minus 2x plus 5. So that's the first part of the way that I split it. And then I have minus 1 over the square root of x . So this one over here, we would just integrate it as the denominator to the power of a half, to the power of minus half rather, and then you add 1 to that and then divide by a half as well. And then here we have to complete the square in our denominator and then see which arc trig or arc hyperbolic function we have to use. So for the first one, the derivative of this, we said this is just the square root of x squared minus 2x plus 5, and then we divide by a half, so that is the same as multiplying by 2. And for the second one here, we said we have to complete the square. So we have minus 1 over, or just dx over the square root. We complete the square. This is x minus 1 squared. And here we have minus 1. Minus 1 plus 4 is, sorry, minus 1 plus 5 is 4. Okay, so we've completed the square, x squared minus 2x plus 1 plus 4. Okay, so it's fine. All right, and before we use the Arc Trig or the other one, this has to be a 1, so we have to factor out the 4, and then we'll have 1 plus something squared, which is the form that we want. So this is 2 square root of x squared minus 2x plus 5. Then minus the integral, we have dx over there. Then we take the 4 out. Then here, just to do more steps in one, I have x minus 1 over 2, the whole thing squared, plus 1. Okay, and then this is all under our square root, like that. Okay, then this square root of 4, which is 1 over 2, can come outside, but we can see that the derivative of the inside here, this x minus 1 over 2 squared, is a half. So the half that is going, okay, we need a half in the numerator. Let me not skip too many steps. X, just do it on the next page. This is 2 square root of x squared minus 2x plus 5, and then minus, we said that in the numerator we need a half, which we have, so it's a half because of this 2 here, so it was a half outside. I can just put the half on top, and then I have the square root of x minus 1 over 2 squared plus 1 dx. Okay, so it is in the form that we want. So now we can just integrate this part. So we have 2 square root of x squared minus 2x plus 5. Then minus, here we have 1 plus something squared, that, and a square root, so that is the hyperbolic sine inverse. This is x minus 1 over 2, and then now we can add our constant of integration. Right, and you can do one more, number 29. We have the integral of x plus 1 over the square root of x squared minus 1 dx. So again, when we have a linear term like this, we want to split it up so that the first part is the derivative of what is here in the denominator, and then the second part we will use our inverse functions to work it out. So this one pretty simple to do because we can just split this as x over this term and then 1 over this term, and the derivative of our denominator is 2x, so then we just have to multiply by 2. So we split it up as x over the square root of x squared minus 1 dx, and the integral of 1 over the square root of x squared minus 1. Okay, then there's a dx there. Okay, my pen is not writing nicely. Okay, so that's dx over there. So this is how we split it up. But then the derivative of the denominator, we say there's a 2 there. So we need to add a 2 there and then a half outside. So this is a half integral of 2x over the square root of x squared minus 1 dx plus the integral of dx over the square root of x squared minus 1. Okay, so this one we can just use direct integration because the derivative, like I said, is the derivative of the denominator is our numerator. So okay, so the integral of this will just be the square root of x squared minus 1. Then you will have to divide it by a half, but then there's already a half there, so the halves will cancel each other out. So you have the square root of x squared minus 1. Then this one here, the derivative of whatever it is you're squaring here is 1, which is there, so you don't need to add anything in the numerator. And we can just go ahead and integrate. When we integrate this, we have x squared minus 1, so that is the hyperbolic cos inverse. So we have hyperbolic cos inverse of x plus c. Okay, so that is how we would do that one. So the rest of the questions in that exercise are similar to at least one of the examples that we did. There are some that is just direct integration. There isn't anything that you have to really do there. You just integrate. Sometimes you will have to multiply by a constant. Other times you will have to complete the square, and then in the last case you may have to split up the numerator that you are given. And then factorize and then integrate like we have done over here. Okay, so our next topic is integration by parts, but I see we have only 5 minutes left, so I don't want to start. Or maybe I will just give the introduction of that so that tomorrow it is not completely new and you can go and read up on it. This is integration by parts. Now, integration by parts is another technique that we use when we're integrating. So as you can see already, differentiation is almost always straightforward, but integration can be a little tricky. There isn't like a one size fits all. Like with differentiation, if it's a product rule will always work. If it's a quotient rule will always work, and so on. But with integration, you may have, they look alike in a way, but the way that you would have to integrate them is different. And the way to actually see how do I go about integrating these functions is practice. So another technique we use for integration is what we call integration by parts. Now this formula for integration by parts, we get it from the product rule. So if you remember, if you have that u is a function of x and v is a function of x, then if you were to use the product rule, you want to find the product of you want to find the derivative of the product of uv. This is uv prime plus u prime v. Okay, now here with integration by parts, what we do is just we integrate everything with respect to x. So I integrate my left-hand side, I have uv prime is equal to the integral of uv plus u prime v dx. And here I'm just left with uv because I'm differentiating and then integrating. So those two cancel each other out. So I'm only left with uv. And this is the integral of uv prime. You can say dx plus the integral of u prime v dx. Okay, or we don't even need to write the dx like that. Okay, and what we do is we now rewrite this as the integral of uv prime. This is equal to uv minus the integral of u prime v du. V. So here everything we're integrating is of course with respect to x. Okay, so what this formula actually means is you actually want to integrate a product where the first term, you have a first term here, and then this second term you have here is something that is the derivative of something else. Okay, it may sound a little bit confusing the way I'm saying it, but when we actually do some examples, it is not that difficult. So let's quickly look at an example. Let's say we want to integrate x sine x with respect to x. Now here, obviously, usually what we would do is try and make the derivative of one of them the other term, and then we can use substitution. But here we have x and sine x. There's no way one is the derivative of the other. So what we do when we're integrating by parts is you need to pick what is your u and what is your v prime or dv. So u and dv or v prime, because you want it in this form. One of them is u and one of them is dv. So how you pick dv, you must pick dv because you're going to have to integrate dv. So you must pick something that is pretty easy to integrate. Here, both of them are pretty easy to integrate, but again, like I say, the more examples you do, you will know, oh, here I mustn't pick this one, even though I can easily integrate both of them. It's best if I pick this one. So here our u is going to be x, and then my dv is sine x dx. So for the rest of the formula, I need u prime, which is du. So I work out du, which is just dx. And then I work out v. So to work out v, I have to integrate sine x dx. The integral of sine x dx is minus cos x. Okay, so now that I have all these terms, I have u, v, I have du or u prime, it's here. I have v, over there, I just substitute them into this formula and then simplify as far as possible. So we say that the integral of x sine x dx, this is u times v. So our u was x, our v is minus cos x, and then we subtract the integral of v multiplied by du. Our v was minus cos x multiplied by du, which is just dx. So what we have to integrate on the right hand side, this is minus x cos x, and then here I have minus minus, which is plus the integral of cos x dx. So this is minus x cos x, and then the integral of cos x is sine x. So plus sine x plus c. Okay, so you can also try it, differentiate this term, and then see, is the answer going to be equal to x? Is the answer going to be equal to x sine x? Okay, so that is the basically how the method of integration by parts works. But we'll look at some more examples tomorrow. I just wanted to introduce it very briefly.